Hello, and in this video we're going to be looking at the gaseous equilibrium constant Kp, and this is for OCR A in your second year of the chemistry A level. This is the reformed specification with the first examinations having begun in 2017, so you can be assured that this is very up to date. A little starter for you, I want you to pause the video and I want you to think about how Equilibria, the position of that equilibrium, is affected by pressure, in particular an increase in pressure. So look at each one of these equations and think to yourself, how will the equilibrium position be affected by an increase in pressure, and how also will the yield of our product be affected by an increase in pressure? The product, of course, being on the right hand side of each equation. So pause the video, have a go at these, and then we'll talk through them in a second. Okay, let's look at A here. We can see that on the left hand side here we have 2 moles of sulfur dioxide and 1 mole of oxygen goes to form 2 moles of sulfur trioxide. Now, whenever we increase the pressure upon a system at equilibrium, Le Chatelier's principle tells us that the position of the equilibrium will shift to counteract that change. So essentially the equilibrium wants to decrease the pressure because we've increased it. Now, to decrease the pressure, it will favour the side with fewer molecules. So essentially what we've got to do here is count the number of molecules. So we can see on this side we've got the 2 here plus a 1 of this, so we've got a total of 3 molecules, and here we've got a 2. So it will favour the side with fewer molecules, which in fact is the right hand side. So this is going to favour the side with fewer molecules, so it's going to shift to the right. And if it shifts to the right, in this case, it increases the yield of our product. Let's have a look at our next example here, the Haber process, nitrogen and hydrogen going to form ammonia. So again, we're increasing the pressure. It's going to favour the side with fewer molecules. Let's think about what side that will be. Okay, so on this side I've got 1 here and 3 here, so that's a total of 4 molecules on this side and 2 molecules on this side. So we can see that again the right hand side is our side with fewer molecules, so it is going to be the favoured side that is favoured, and therefore the yield of our product, ammonia in this case, is going to increase because it shifts right to decrease that pressure. Let's have a look at this example here. It looks like a decomposition of some kind, and we can see here that we have got, let's get my pen back, we have got 1 molecule of this on the left hand side there, and we have got 2 molecules of the nitrogen dioxide there. So it's going to shift to the side with fewer molecules, which is actually going to be the left hand side this time. And rub that out so it doesn't get in the way of the text. So there we go, it's favouring the side with fewer molecules. In this side is the left, and if you shift left, then ultimately you're going to decrease the yield of your product because we're going this way now, away from it. Okay, and then finally the manufacture of hydrogen iodide, example D over here. So we can see that actually this is an interesting one because I've got 1 of this and I've got 1 of this, which is a number of 2 molecules here, and I can see that I've got 2 molecules over here. So we're increasing the pressure, increasing it, but actually when we look here at our example, there is no side overall with fewer molecules. So there's only one thing we can really say here: there's an equal number of molecules each side, therefore there's no change in the equilibrium position because neither side is favoured. Okay, in this case it would ordinarily favour the side with fewer molecules, but neither side has fewer molecules than the other. So this is one that we cannot provide a qualitative answer on other than no change whatsoever. Okay, so what we're going to be doing is looking at a different kind of equilibrium constant today. It's called Kp, and we're going to learn how to write expressions for Kp, much as you would have done for Kc before, and then how to calculate Kp using things called mole fractions and partial pressures. Hopefully this will be very easy and very straightforward. Let's go ahead. Okay, so my first question is going to be, what is Kp? Well, Kp is an equilibrium constant that is used for systems that have gases, okay, composed of gases, so gaseous equilibria. And Kp is used instead of Kc because Kc is quite difficult to calculate for gaseous equilibria because ultimately you need concentrations, and it's difficult to find out what the concentration of a gas is. It's very difficult to calculate the number of moles in a unit volume when you've got something as random and as chaotic and as populous as a gas. So we would instead use Kp because it's difficult to find concentrations, and Kp doesn't use concentrations. Kp uses something called partial pressures, A just being whatever species we're looking at there, instead of concentrations. So here's an example of a gaseous equilibria. We recognise realise it's a gaseous equilibria because of the state symbols G underneath each of the species given there in the equation. Now, if we were to follow the traditional route and write an expression for Kc there, this is a Kc expression. We would say that it's the products, and then they are raised to the power of their coefficient divided by the reactants raised to the power of their coefficients, the 3 there and the 3 there. And these square brackets denote the concentration of each species, and we would derive those concentrations by dividing the number of moles of each by whatever the volume of that container might be. As I've just said, it's very difficult to find the concentration of a gas, so this is almost an irrelevant expression to write in this case because it's not the expression for the equilibria that we would use in practice. So instead we're going to use Kp, and Kp, we can see an expression for Kp here. Now what you will notice to start with is it's actually very, very similar to the expression for Kc, except rather than using square brackets, we're now using rounded brackets, and there's a little lowercase italic p in front of each one of the species, and p with its little brackets, so p and then brackets, something within, that denotes a partial pressure. Okay, that's called a partial pressure. So instead of looking at the concentrations of each, we're looking at their partial pressures, and you will still notice that we raise to the power of the coefficient. So just as we had in the expression for Kc, we're going to raise to the power of the coefficient here in our expression for Kp. And we would calculate our partial pressures of each species, not by dividing number of moles by volume, but by working out what fraction that number of moles of that species is of the total number of moles, then multiplying that by the total pressure of the system. So it's a bit like a concentration, but a concentration for a gas out of the whole. And we're going to look at how to calculate partial pressures now. Okay, so what is a partial pressure? Well, essentially, if you've got a number of gases all within the same space, the same volume, a partial pressure is how much does each gas contribute to the total pressure of that system. So I want you to imagine yourself in a room, and there in that room there are some twins, and then there is you. Okay, so you're in a square room and there's a pair of twins, and then there's you. Well, in the total number of molecules in that room, you make up 1/3 of the total pressure essentially within that room, whereas the twins make up 2/3 of the total pressure. And it doesn't matter how big you are, you might be a bit fatter than the twins, it doesn't matter, because what PVNRT tells us is that the identity of any gas is insignificant to the volume or pressure that it occupies at a fixed temperature. Okay, so it doesn't matter whether you are a very light gas like hydrogen or a very heavy gas, I don't know, like something like sulfur dioxide. It doesn't matter which one of those two gases you are, because the same number of moles of each will occupy the same volume. Okay, so what we can do is we can actually use the fraction of the total number of moles of any gas and the total pressure to work out what its partial pressure is. So I want you to imagine now, rather than this room, the atmosphere of Neptune. Okay, planet quite a lot further away from Earth. It's got a total pressure of 10 kilopascals there as a size comparison for you. Now I looked online and I found out that actually Neptune's made out of a lot of hydrogen there, so it might be a valuable energy resource one day for a clean source of energy. Okay, but it's 80% hydrogen, it's 18% helium, and then it's got a little bit of methane. Now there are some gases, other gases there as well, but I rounded this up to 100 to reduce any complications there. Now, what we've got to do to start with is calculate the mole fraction of each gas. So that's how many moles out of the total number of moles does each gas make up. Okay, so this is very, very simple. We've got 80 here for hydrogen, so it's 80 out of 100, so its mole fraction is 0.8. Okay, same for helium, it's 18 over 100, so its mole fraction is 0.18. And then finally, methane is 2 out of 100, so its mole fraction is 0.02. Now, one of the things that OCR or other exam boards might do is they might deliberately make it such that there's something else there. And if you've divided each mole, if you've worked out the mole fractions, you should notice that there's something else there. So it's really important that the sum of mole fractions adds up to 1. Okay, if it doesn't, then there's another gas there, and it will be somewhere written in the question, and you've got to account for the fact that that gas is there. So do a little check for me when you finish these, that you always add up your individual mole fractions and you confirm that they add up to 1. If they do, then we are good to go ahead. Okay, so now that we've got the mole fractions for each one of these gases, we are now going to calculate the partial pressure. And all the partial pressure is it's the mole fraction multiplied by the total pressure. And that will tell you how much each gas contributes towards the total pressure. So we've got here the partial pressure of hydrogen. See how we've written it there? Lowercase italic p, open curved brackets, and then just the formula of that species is equal to its mole fraction. There it is, 0.8, multiplied by the total pressure, so 10 kilopascals on the surface of Neptune there. Okay, so when we do this multiplication, we find out that hydrogen contributes 8 kilopascals, helium contributes 1.8 kilopascals, and that's supposed to say methane. Clearly it doesn't. It's let's just change that quickly. Let's cross that out. CH4. Sorry about that, guys. I'm not going to re-record it though. There it is. Partial pressure of methane is 0.2 kilopascals. Now, just as I did previously, I need to confirm now that the partial pressures, the amount that each gas contributes towards my total pressure, adds up to my total pressure, because if it doesn't, there is something else there. Okay, so let's add those up quickly. We can see that 8 plus 1.8 plus 0.2 is equal to 10 pascals, which is the same as my total pressure. There it is. It's all the same. Okay, so I've done my checks. It's really important to show your checks. Sometimes marks are available for doing this. Okay, so do make sure you perform those checks in these calculations. It is standard practice. Okay, so now we've got partial pressures and I've shown you how to calculate mole fractions. Let's go on to how this would be used in an example for calculating Kp. So now we've got an example of where you are expected to use information about the number of moles, information about the total pressure of a system to calculate Kp. So we can see here we've got that classic reaction that you've seen all the way from GCSE, hopefully, all the way through your A levels, and you will continue to study at university if you do chemistry there. So we've got the Haber process. It's used to produce ammonia. 1 molecule of nitrogen reacts with 3 molecules of hydrogen to produce 2 molecules of ammonia. Classic process. The ammonia is then used in fertilizers typically, although it did used to be used for making explosives. Okay, so we can see here it uses a very particular temperature and pressure of 400 degrees Celsius and 200 atmospheres respectively. The equilibrium mixture is found to contain 9 moles of nitrogen, 27 moles of hydrogen and 24 moles of ammonia. Calculate Kp. Great. Now this is good because I can see that this is the equilibrium mixture. This isn't my starting initial amount, so I don't need to use an ICE table in this example. If this was the starting mixture and they'd given me one of the species at equilibrium, I would now need to calculate equilibrium amounts using an ICE table. But in this example I do not, because this is my equilibrium mixture. So these numbers are going to plug straight into the Kp equation after they've been turned into partial pressures. So what we've got to do to start with is write an expression for Kp. So we do it as we always have done. Okay, so we're going to write the lowercase italics p with the species there in its open brackets. I'm going to write the state symbols in as well, just as best practice. And I'm going to raise each of these partial pressures to the power of the coefficient. So a 2 here because there's a 2 in front of ammonia, a 1 here effectively because there's nothing in front of the nitrogen, and a 3 here because there's 3 in front of the hydrogen. Okay, so I've written here the expression for Kp, suggesting partial pressures used for each of these, but now I need to work out what the partial pressures might be. So, to work out a partial pressure, the first thing you need to do is calculate the mole fraction of each species. Now, I have the number of moles of nitrogen, hydrogen, and ammonia, so I need to know what fraction each one of those moles is of the total number of moles. So the first thing I'm going to do is add up the total number of moles in that system. So I've got 9, that came from the nitrogen, plus 27, which came from the hydrogen, plus 24, which came from the ammonia. So that's my total number of moles. I've got 60 moles in that system. So 60 people in the room. Think of it like that. So now what I'm going to do is work out what fraction each one of those gases is of the total number of moles. It's mole fraction. Okay, so the first one, there's nitrogen, 9 over 60, 0.15. Hydrogen, 27 over 60, 0.45. And ammonia, 24 over 60, 0.40. So you can see there that we've worked out the fraction that each one's number of moles is of the total number of moles, and as always, convention, we're going to now check this by adding them up and confirming that they add up to give the number 1, and they do. Okay, 0.15 plus 0.45 plus 0.40 is equal to 1. So that's great. The check is complete. Now that we've calculated the mole fraction of each species, we simply have to multiply by the total pressure to work out the partial pressure of each species. So let's do that now. Okay, so we've got to calculate in the partial pressures. So the partial pressure of nitrogen is equal to its mole fraction here, 0.15, times the total pressure, which the question said was 200 atmospheres. So I'm going to do 0.15 times 200 gives me 30. Great. Now I'm going to do the hydrogen here. 0.45 times the total pressure gives me 90. Great. And then finally the ammonia here, 0.40 came from the mole fraction over here, times 200 atmospheres gives me 80. Again, I'm going to perform another check. I need to check that the sum of my partial pressures adds up to give my total pressure. If it doesn't, there's something else there. It does. Lovely. Okay, so now I have my partial pressures for each one of the species in my equation, this here. So what I can do is I can now plug these numbers here into my Kp expression and raise to the power of the coefficients and then calculate my units. So let's go ahead and input the values. So we just confirmed that the partial pressures of each species were as follows by multiplying the mole fractions by the total pressures, and we checked that they were correct by adding them up and confirming they gave the sum of the total pressure. We're now ready to input these values into the equation and raise to the power of the stoichiometric coefficients. So we can see here that I've got first the partial pressure of ammonia. That was this one here. There it is. I've now got the partial pressure of nitrogen. That was this one here. And I've got the partial pressure of hydrogen. That was this one here. And in the case of hydrogen, I've cubed it because it's a 3 in the equation. And in the case of ammonia, I've squared it because it's got a 2 in front of it in the original equation. I'm also going to calculate the units at the same time. I'm just going to give you these here. So I calculated this to give me 2.9 times 10 to the minus 4 atmospheres to the power of minus 2. Now, if you've seen my other video, you'll know that units are incredibly important, but some of you might still be struggling with calculating the units for this. So I'm just going to show you how I would do that quickly. We can see on the top here, I've got atmospheres to the power of 2. Okay, so the top of my equation I can treat as n to the power of 2. Where every time I've got n, it's equal to an atmosphere. On the bottom of my equation, I've got a 1 here effectively and a 3 here. When we multiply indices, we add them. So I've got 1 times the 3, which gives me n to the power of 4. Now I'm dividing indices here, so I take away 2 minus the 4 is equal to minus 2. So I end up with n to the power of minus 2, which is the same as saying atmospheres raised to the power of minus 2. That's a 1 there. When we multiply indices, when we raise one index to the power of another index, we multiply, we don't add. So this is atmospheres, 1 times minus 2, atmospheres to the power of minus 2. That's how we got the units there. If you're still struggling with units, you should watch my video on Kc, as there are some examples of how to multiply and divide indices in that video. Right, I'm just going to clear this quickly, but just to let you know that the acceptable values of units for use within the Kp expression are pascals, kilopascals, and atmospheres. They're the most standard used in chemistry. Okay, that was a homogeneous example because everything within that equilibrium was in the same phase or state. In this case, it was a gas. But sometimes you'll have gaseous equilibria whereby some of the species might be solids or some of them might be liquids. And as we know that if we were to compare the concentrations or partial pressures, in fact, of let's say a liquid with a gas, the liquid would be so much denser that it would have several orders of magnitude higher a concentration or higher a partial pressure than the gas. Therefore, they wouldn't be comparable and it would completely dwarf the figure of Kp. So whenever we've got heterogeneous systems, we omit solids and liquids. We do not include them in the expression for Kc. So we don't include them because their concentrations or partial pressures are effectively constant where they're so much larger than that of a gaseous or aqueous species. So look at this example here. Now some of you will know this reaction if you bleach your hair. Okay, so anyone who's ever had highlights done to make a bit of their hair blonde, or they've completely bleached it, great, you'll know about this because this is hydrogen peroxide here. It's an oxidizing agent. And also you'll know of this if you've ever seen your teacher do the experiment which is elephant's toothpaste, where they chuck a little bit of potassium iodide as a catalyst into a conical flask or a measuring cylinder full of this and some washing up liquid, and it produces a gas here, the oxygen. And as this reaction produces the gas, it typically fills up it fills up the fairy liquid, and it creates loads and loads of bubbles, and it froths up all over the table, and it's lovely. It's a great fun experiment. Okay, so it produces a gas here, and it's a reversible reaction, not very readily, but it is technically a reversible reaction. And we can see here it's classed as a heterogeneous equilibria because we've got things in different states here. We've got liquids and we've got a gas. Now, if we're to write an ordinary Kp expression for this, then yes, we would do products divided by reactants raised to the power of their stoichiometric coefficients. However, two of these species must be omitted from the Kp expression because they are not in the right state. They are liquids. Same, you do this with solids as well. So we're going to omit those two liquids. Now, what this essentially leaves us with is Kp is equal to the partial pressure of oxygen. And you might be thinking to yourself now, if you've got a little bit of logic here, well, the partial pressure of oxygen is technically the total pressure of the system if we're looking just at gases. So it's quite an interesting case this, because it's the only gas, therefore its partial pressure is 100% of the total. Yeah, so the partial pressure of oxygen is equal to the total pressure, which actually means that in this case Kp is simply equal to the total pressure of the system. So whatever the pressure of that gas is, that's actually equal to Kp. So just a weird example there of how you can get strange and unique answers when you've got heterogeneous equilibria going on. Okay, so let's recap this finally. So Kp is used to indicate the magnitude of the equilibrium position for a gaseous system. Okay, so it tells us how far to the left it lies or how far to the right. So anything lower than 1 tells us that the equilibrium lies towards the left, towards the reactants, because the number on the bottom of the Kp expression is going to be larger. Anything greater than 1 tells us that there are more products than reactants, so the equilibrium lies towards the right. In a heterogeneous equilibria, you've got to remove anything other than a gas, okay, or an aqueous species, but this is gaseous equilibrium, so we're just talking about the gases here. Anything other than a gas is excluded, okay? Now, we're going to use in a Kp expression, we're also going to be using partial pressures instead of concentrations, and we still raise those to the power of the coefficient given in the equation. We calculate a partial pressure by multiplying the mole fraction by the total pressure of the system. We can use the units of partial pressure as pascals, kilopascals and atmospheres, and we've got to check that our mole fractions add up to give 1 and our partial pressures add up to give the total pressure. As always, my final warning, make sure you look at the links in the video description below and you now do some practice. I've never known a chemistry student that can achieve great results unless they practice what they're doing. So use the links below, have a go at these, go through the answers yourself, make sure you've nailed it, and thanks again for your time.